right. Okay, so bainite, not to put too fine a point on it, but bainite there's so much we don't understand. It's even hard to differentiate. If you just do some EBSD or optical microscopy or some SEM backscatter and secondary imaging, it's very difficult to sometimes tell bainite from ferrite, and sometimes it's very difficult to tell bainite from martensite, right? It's not easy. And so there's a quote here, and I don't know who to ascribe it to, unfortunately, but I've seen this repeated a couple times. It says bainite is halfway in between decent perlite and fully developed martensite, right? And in the German word for it, Zwischenstufende Hüge, the umlauts, the umlaut U means you kind of have to make your mouth like a horse shape, right? But that actually literally translates to in-between step structure, right? So bainite is this weird kind of halfway in-between thing. It has a definite shear, but then it also has carbides that form by diffusion, right? And the thing that makes it really interesting is there's a lot of dislocation-rich ferrite because of the shear, the plastic deformation. That shear has a large characteristic. There's a shear that happens, which gives rise to a large stress, right? You can imagine if I have a lattice that suddenly goes like this, right? It's like a 12% shear, whereas elastic strains are typically on the order of, 0.2%? So that means that other 11.8% shear has to be accommodated by dislocation plasticity, right? So something similar happens in martensite. So we have this very dislocation-rich ferrite structure, and so the ferrite present in the bainite is much harder than ferrite present in perlite, right? So we have a kind of similar composite structure of cementite and ferrite, but here we've got this added distortion. And we'll talk about it more, and it's not 100% clear whether bainite happens in a diffusionless manner, and then the diffusion happens after the fact, or if there are some diffusion-mediated mechanisms to bainite formation, right? So these are all things that we just don't know. Okay. So bainite kind of happens at in-between temperatures. If we're at higher temperatures, we get perlite. If we're at lower temperatures, we get martensite. Right? And so at this intermediate temperature range, depending on the alloy, sort of 250 to 500 C, we get these fine ferrite and cementite particles known as bainite, right? So we have this fine ferrite lath here with cementite, and like perlite, they sort of have this regular spacing sometimes, right? And then this is what we would call upper bainite. Lower bainite, you get cementite, even smaller fine cementite in the ferrite regions as well, right? And so you can sort of see the sort of a schematic of perlite and bainite formation here, right? So perlite and then upper bainite and lower bainite. We'll talk about the differences of upper and lower bainite. And I like this, the source where I got this from here is, Metallurgy for Dummies, where I shamelessly stole this picture from. Right? And so if we look at where we are on our CCC curve, right, we're sort of down here, right? And so we have, if we look at this is a TTT curve, this is more of a CC, continuous cooling, where if we see, here's our ferrite and perlite nose up here. If we come down, our martensite kind of comes into here. So we see this sort of decomposition in a lot of alloys like this iron carbon manganese, where we see two noses, one for reconstructive and one for displacive. Right? And if we come in down here, we're into the bainite. This is, of course, the martensite start temperature here. Right? It doesn't matter how we cool it. Right? If we cool fast enough and we miss this nose, we're going to hit martensite. So it's a non-lamellar aggregate of carbides and plate-shaped ferrite, right? It turns out that the carbide part is not really the essential processing here, right? The carbides form after the fact, right? So we have a transformation from austenite to ferrite that happens with a characteristic shear, and then we get these plates of cementite that form, right? So we know the cementite forms in a diffusional way, right? But the question is, when I say is it a diffusionless or a diffusion-mediated transport, is what happens to the carbon? Does the transformation happen fast enough that the carbon isn't rejected, or does it happen in a kind of para-equilibrium state like Widmanstätten does, where the carbon is diffused out and the shear happens? So upper bainite, you get these ferrite regions that are largely free of carbides. Lower bainite, we have residual carbides that form in the ferrite regions. These are cementite. Yeah. Right. Okay. So why is bainite so confusing? Right. Nothing that I said so far should strike fear in anyone's heart. Right. It doesn't appear to be too much different than Widmanstätten, except nucleating in smaller little packets rather than growing in from grain boundaries. But really, it has a dual nature, right? And this is why we say it's halfway in between austenite or perlite and martensite, right? So we have a compositional change, and it requires the long-term diffusion of carbon. So it's different than martensite, right? It's not athermal, right? We'll talk about next lecture is austenite and martensite. But the formation of bainite requires an incubation time, right? And when we hold it isothermally, we get a typical nucleation and growth curve, right? But notice it doesn't go to completion, right? It goes to a value that depends on the cooling, right? So if I were to lower it down, right, I have like martensite, I have a bainite start and a bainite stop temperature, right? So it has properties of nucleation and growth, but it's also shear and has a characteristic start and stop temperature like an athermal transformation. So part of it behaves like isothermal, part of it behaves like athermal. It's a little wonky. All right? And so we can see here that the Right, so we do have incubation time, right, depending on the alloy and the temperature, right? And so we can come down isothermally, and for 5, which in this case is at 422 Kelvin, so that's pretty low, but you notice we have a time of several hours before we see any bainite formation, right? So bainite, right, so here's percent bainite. This is temperature. So as we're cooling, right, if we're above the bainite start temperature, oops, right, we won't get any nucleation at all, right? And if we cool it down, we get a amount of transformation that depends on the temperature, right? So at temperatures between the bainite start and the bainite finish, we're not going to go completely to bainite. Both nucleation and growth stop before all the austenite is consumed, right? Which is a lot like martensite, right? So this bainite finish is not really a well-defined thermodynamic temperature. Right, it's kind of sort of experimentally where we observe things finish up. We can't necessarily pin it down. So we have a finite number of nuclei that have to grow. They have to grow to bainite plates. Okay, so we can, if we're in between the bainite start and the bainite finish temperature, we're not going to go completely, right? Both nucleation and growth has to terminate, right? The limitation of growth, we can understand that, right? If we nucleate a plate and then it grows, it can either grow until it intersects another plate or hits a grain boundary, or because I said that there's a large shear that needs to be accommodated, right? And it leads to plastic deformation. That plastic deformation can lead to the interface becoming decoherent, right? And then you're not able to continue growth. So we can come up with mechanisms that make sense why the growth of these plates. Nucleation stopping is much more complex. We'll get to that on slide 23, right? But we'll talk a little bit about some of the features of bainite before we get into this diffusional versus diffusionless debate a little bit more. Okay, so upper bainite, the microstructure is these plates that grow in clusters that we call sheaths, right? So within a sheet we have plates that are parallel and have the same crystallographic orientation, right? And they're either going to be, the sheets are going to be separated by a low angle boundary or cementite particles, because they're going to be approximately the same crystallographic orientation. So the bainite, upper bainite begins with nucleation of these ferrite plates at the gamma grain boundaries. Each plate grows with a change in shape that has this invariant plane strain and a large shear component, right? That's very reminiscent of what we're going to talk about with martensite, right? And here's just some different microstructures, right? We can see the individual plates with the carbide particles in between. And so we have, it grows at a higher temperature than martensite. On a polished sample, we see surface relief, right? Because we have these shears, and then this large shear has to be accommodated by plastic deformation, and that plastic deformation is going to limit the growth of the ferrite plates, right? And so these plates end up being much smaller than the prior austenite grain size, right? So here's some old TEM images, and you can see the large dislocation density that forms, right, that's associated with the formation of this bainite ferrite subunits, right? So bainite first forms via displacive mechanism, right? So then we get diffusion accompanying the formation of ferrite, right? So shear, then we diffuse the carbon out to make ferrite and cementite, right? So bainite. Well, you go from austenite to a supersaturated ferrite. Then you have, how supersaturated it is depends on what mechanism you ascribe, whether it's diffusional or diffusionless. If it's, let's just say it's diffusionless, you have a shear transformation that goes from austenite to supersaturated ferrite, then diffusion of the carbon out of the supersaturated ferrite to form cementite at the interface, right? And so basically what you have here, right? So this is the supersaturated ferrite, this alpha prime, right? So you get the shear, right? And then that would lead to a big kink, just like in Widmanstätten, right? But in Widmanstätten, we nucleated a variant with the opposite sense shear. Here, you get slip, right? You have plastic deformation that accommodates this large shear, right? And so here's atomic force microscopy scans, right? Where you get the surface relief, right? And you can see you get austenite that's relatively flat, you get the surface relief from the shear, and then you have rough on the back side of it where all your dislocation slip, happens. Okay? So the formation of the ferrite subunits from the supersaturated alpha prime, right? We get diffusion of carbon into the adjacent austenite, right? And when the carbon concentration reaches a critical value, we get the carbides that form, right? So we have these subunits, and then we have a sheaf, right? And the subunits grow, nucleate and grow, the carbides come out in between, and then the sheaf still growing. And this happens pretty quickly, right? We're at a temperature where this diffusion, the formation of carbides, especially in upper bainite, where we're at a slightly higher temperature, can still happen relatively quickly, right? Slower than the shear transformation for the subunit, but slower than the growth of the entire sheaf. Okay. If you have cementite retarding elements like aluminum or silicon, then you can get bainite that forms, upper bainite that forms without the formation of the cementite, right? So what you end up then is you have ferrite subunits with carbon-enriched austenite in between, right? So if you have an austenite stabilizer, like aluminum or silicon, right, you're not going to necessarily form the cementite. That was why I said that the cementite is not a structurally necessary component of bainite, where it is with perlite, right? Perlite is this composite of ferrite and cementite that grew diffusionally, right? Bainite can be formed without the formation of cementite, right? And this is again goes to why bainite is so tricky, right? This diffusion is happening quickly enough, right? It's not like you can observe it's very difficult to observe in situ, right? In martensite, you get the shear transformation, then you can cool it. You cool it down, and then you look, and when you do metallography at room temperature, you see that the carbon concentration in your martensite is the same as it was in your austenite, right? If you don't temper it. Bainite happens at a high enough temperature that the carbon still has enough mobility that you don't know whether it's all happening simultaneously or what exactly the kinetics of all these little sub-processes are, because you only see it after the fact, after it's diffused out and these carbides have grown, or this carbon-rich austenite has formed, and you don't see any more of the alpha prime regions left. So lower bainite happens at slightly lower temperatures, but we have less extensive diffusion of the carbon. So carbides are going to form in between the ferrite subunits, but also inside the ferrite, right? So we'll have small carbides, either cementite or other particles, right? So the cementite in the supersaturated ferrite forms that Bagriatsky OR, and I meant to look that up and I forgot, but I will definitely get to that. There was my notation for the orientation relationships for Widmanstätten might not have been 100% consistent, and so I want to go back and double check that because there were some questions. Which makes me wonder why no one picked up on that last year, but this year there were a couple questions, which is good, right? Right. So here we see this is within one subunit, and we can see the carbides, right? Sheaves of lower bainite, and then TEM of the carbide precipitates within a single, right? So this micron bar is 500 nanometers, half a micron, the scale bar. So we can see that the carbides that form within the individual ferrite subunit are quite small. So cementite is Fe3C, right? Right. There are Hague carbides and other carbides that can form. We can't differentiate them optically, right? You would have to do diffraction in the TEM to be able to tell them apart. This is, these are optical, right? So this is 20 micron, right? So this is a bunch of lower bainite subunits, right? These are sheaves, right? Then down here, this is a TEM micrograph. This scale bar here is 500 nanometers, where we're looking within one lower bainite ferrite subunit. and these are the very fine carbides. Most likely cementite, but you can have other carbides that form in there. Right? So most of the time, but not always, right? The cementite and the lower bainite forms with ferrite subunits of only one orientation. It's like one variant of this orientation relationship, and so you get parallel arrays of particles, but that doesn't always happen. Right? So our kinetics, right? This is our TTT, right? And generally here, right? So the reconstructive transformations are up here. So if we have this nose, we can kind of split the region where we form upper bainite and lower bainite into these regions. Okay. So as I said before, we really don't know whether bainite forms in a completely diffusionless manner, or there is some diffusion that happens during transformation, right? Experimentally, we see that carbon has partitioned into the austenite, right? Or grown into cementite or other carbides, right? But as I had said, when we do a martensite, it's pretty easy to determine that it's diffusionless because the carbon content of the martensite is the same as the original carbon content of the austenite was, right? As long as we don't temper it. Bainite forms at a higher temperature where we still have carbon can diffuse, right? If you just do sort of square root dt, and the plate that's only a couple microns wide, right? Those diffusion distances is still less than a second, right? So it's impossible to tell whether we're to measure that directly, right? We can't freeze, right? Quench in that carbon into the bainite structure. Okay, so there's a couple options, right? So we can have a case where the carbon partitions during the growth of the subunit so that the ferrite doesn't ever contain any excess carbon, in which case we don't go to that alpha prime structure that I showed. It just goes from austenite to ferrite by a shear transformation, or accompanied with the carbon diffusion, right? The other extreme is that with being diffusionless, the carbon is trapped by the shear transformation and then diffuses out after. Or you can have an intermediate case, right, in which some carbon may diffuse with the remainder being trapped, right? There have been mechanisms that have been proposed where you need a fraction of the carbon to diffuse out, and then you transform the rest of the way by shear. So it's difficult to determine the precise role of the carbon. I'm going to go through the main arguments for either the diffusion-controlled reaction model or the diffusionless, right? It'll probably be pretty obvious that my personal feeling is that it's a diffusionless transformation based on what I think is the more compelling experimental evidence, but I'm not an expert in steel. I'm definitely not an expert in bainite, right? So someone, right, I can just say it's not completely settled. I find the diffusionless to be a diffusionless mechanism to have more compelling experimental data, right? But if we look at the diffusion controlled, right, so we have this essentially a non-lamellar analog to perlite, right? So our bainitic ferrite grows by diffusion-controlled movement of the ledges along these alpha-gamma ferrite plate boundaries, right? And it's pretty much the same as Widmanstätten growth, right? So the carbon concentration in the ferrite is going to be low, the austenite gets enriched, and then the carbides nucleate on the austenite side of the austenite ferrite boundary, right? So if we're growing and we're partitioning carbon out of the ferrite, the austenite's going to be carbon rich, and so like the sympathetic sideways nucleation, we should grow our carbides from the austenite side of the interface, not the ferrite side of the interface, right? But there's been some experimental studies that show it. Getting ahead of myself. So this is what the experiments that have been done, where they've done in situ growth in the TEM, right, have shown that for upper bainite. But when they do lower bainite, they see that the carbides form on the ferrite side of the interface, right? So it's a little inconclusive, right? The diffusionless transformation model, I think, is more compelling, but this argument is a little more complicated. And I have to admit, when I was a student, when I was sitting in your guys' seat, this didn't make any sense to me, right? It wasn't until after I had graduated and was doing other things that I finally and I'll explain to you what I was missing from this argument, because it's a really simple little bit of interpretation, and without it, it doesn't make any sense. Okay, so if we're having a diffusionless phase transformation, right? We're going from austenite to ferrite without any partitioning, right? That means we're moving on here's our double wall potential. We're moving from our austenite curve down to our ferrite curve, right? Okay, so does it make sense that it's not going to happen if the free energy of my austenite is not lower than the free energy of my ferrite, right? So that means I have to be in a higher state of free energy in austenite, and for the same carbon concentration, I have to fall down, right? If I'm over here, my austenite is lower free energy than my my ferrite. So I'm not going to transform, because I'm going to be going up. This was the key thing that I was missing from understanding this whole concept. Because what people do is they make a statement like this is out of Harry Badish's book, right? They say that to be diffusionless, the transformation must occur at a temperature below T0, right? Where the free energies of the two phases are equal, right? So essentially what it's saying is this is the highest point on this curve where this can happen, right? And if we plot as a function of temperature this T0 line, right, we have to be transforming at a temperature below this T0 line for this to occur. But really the argument is my free energy when I go from austenite to ferrite had better go down without partitioning, right? So what happens? I can go from here, I can drop to here, I'm still at the same concentration, then I will partition into ferrite of this composition and austenite of this composition, right? Or I can grow cementite, right? Right? That's not on here as well, right? That third curve would be a little bit. So that means essentially all of my Bainite nucleation has to happen between this AE1 curve and this T0 curve. Right? Again, the T0 is where the intersection between the austenite and ferrite free energy curves. Right? And this is essentially exactly what is observed experimentally. Right? So if it's diffusionless, the carbon would be rejected from the alpha prime after formation, right? So we nucleate, we grow, then the carbon diffuses out. That means the next sheaf that grows, it's rejected into the austenite, the next sheaf that grows is going to be nucleating in a slightly carbon-enriched environment, right? And as the sheaf grows and more subunits go out, the carbon content outside of that region gets to a point where our concentration is now over past this point, and the next sheaf that would nucleate would have to increase its free energy for that particular carbon concentration, right? And so essentially, this is what we see. Experimentally, the Bainite reaction does stop at carbon concentrations corresponding to this T0 line, right? Okay. The other thing about this is it goes a long way towards explaining the Bainite start temperature, right? Because this T0 temperature increases, this T0 point increases with carbon content as the temperature is reduced, right? So as the transformation temperature cools, we have more Bainite that we can form, right? So basically the Bainite start temperature would then correspond to where the triple point between this AE1, AE3, and T0 line, because this T0 line always has to lie between the two equilibrium, right? The double tangent, right? If we're doing the double tangent, this intersection point has to lie in between those, right? So that's essentially the diffusionless transformation idea, and I think it's, I like it philosophically, right? Because there's nice thermodynamics kind of rationale behind it, and there's good experimental evidence, but there are lots of people who think this is bunk, right? People who spend a lot more time researching in steel than I do, right? You know, if you look at what I've done in steel, it's mostly computational work, all completely computational work on understanding, reconstructing martensite structures, right? So going back, right? So steel is not my strong area of expertise, and Bainite sure as hell isn't. So, right, maybe someone will come up with a much better answer. But you know, if we think about it from the double well potential, and understanding that if you're above that, the T0 composition, the intersection, your local free energy has to increase by the transformation. It seems to make a lot more sense. Okay, so the kinetics of this, right? So we have a subunit that forms. You have the shear transformation, and then it is essentially halted by the plastic deformation, right? This shape change, right? So then a new subunit nucleates, right? And then we have this sheaf structure that develops, right? And the overall growth rate of this whole sheaf is slower than the growth rate of the individual subunits, right? We have a subunit that grows very quickly and stops. Then we wait for a little bit, and then we nucleate another sheaf, and it stops. So the overall lengthening that you would see by, say, optical microscopy is much slower than this subunit. Right? And then right, the transformation occurs more slowly at higher temperatures, right? We have less driving force, right? And the plastic deformation, which limits the length of the subunits, occurs more easily, right? Because we have right, less resistance to dislocation motion, right? So we have easier plastic deformation. Then after this, the carbides will eventually form, right? So because of this, the bainite looks like a nucleation in growth because we have an incubation time or a nucleation time, right? Which is really this waiting time for these individual subunits to form, right? And so on our TTT curve, we sort of split. We have this reconstructive regime and then this displacive, right? And then right, this is right. If we lower the transformation temperature, right, we can transform from upper to lower bainite, right? So we can, if we're continuously cooling, we can start nucleating, start by growing upper bainite, and then as we go down, we'll transition to lower bainite with these particles. And one point that seems a little counterintuitive first, right? These carbides are very, very fine, right? But you have less in between the sheafs, and this cementite that's in between these subunits is a good spot for crack initiation. So even though it seems weird, you've got these fine distribution of carbides, this lower bainite actually is tougher than upper bainite, and it's also stronger because these are effective strengthening particles as well, right? So as you cool your transformation, you gain in strength and you gain in toughness. Bainite usually is at a much lower temperature, but as we'll see when we do, depending on what your cooling schedule looks like, you can go through the perlite regime and then potentially into bainite, right? Which is another reason why it's potentially difficult to sort all these things out. Okay, and then related, right? We have acicular ferrite, and I'm not going to jump into this. So we'll discuss acicular ferrite and how it's related to bainite and this tempering of bainite on Wednesday, and we'll start with twinning and martensite on Wednesday.